is Slava Masle. Yeah, my name is Slava Maslennikov, and I'm with ISO New England with Research and Development Department for last 19 years. Before, I was a university professor in St. Petersburg, Russia. So my relation with this working group is probably from the very inception of the group, was always involved and continue and hope to be a contributor in the future. So for this presentation, half of our audience already familiar with majority of the stuff, at least Bean, Matt, and Jim have seen major part of this presentation. So sorry for the repetition. It will be old stuff, but for the rest, probably it's something new. Okay, so a presentation is titled Oscillation Management. And typically people discussing finding the source or characterization, but really objective is, and I'm expressing my presentation is from point of view of ISO, system operator, on what to do with oscillations. So, and objective is to mitigate oscillation. So objective is shown on the slide. First of all, detection and mitigation. So from that perspective, whatever we do, whatever is necessary to mitigate oscillation. And if you are talking about forced oscillation and actually natural, to up to the moment for the traditional power system, problem is reasonably well solved for traditional oscillations, because again, I'm talking from point of view of ISO New England, which is part of Eastern Interconnect. But almost 100% of oscillation we observed are forced oscillation. And identification of source of the forced oscillation is actionable information for mitigation. So, and that's what we have at ISO New England. We have online automated oscillation management system, which is operational since September 2017. It's production grade process with exactly same objective: detect oscillation and identify who is responsible, find the source, and send information to operational personnel. So during the lifetime, the process, this automated process actually went through more than 1,000 oscillations automatically with nearly 100% success rate. So it works like use PMU data from more than 40 locations across the system. Then it's run detection and oscillation source location algorithm and send all information with attachment to list of recipient who is the list in the recipient of that notification list. Here is an example for event which happened July 23. That was 0.2 Hertz oscillation caused by excitation system of one of the generator inside of New England. This is a copy of a real email which was sent that time. And that is timeline, time series, how oscillation look like. What is interesting to point out that magnitude of reactive power was twice higher than active power. And this is a part of results of OSL process, visualization of dissipating energy flow, showing which generator is the source. Then that process identified what type of control system is responsible as a source. And that is a pattern recognition algorithm, which is converting dissipating energy flow pattern into specific message. Specifically here, it's identify which area is the source, which specific station, and which specific unit is the source. So that information, as I said, is automatically generated after 1-2 minutes after oscillation is detected and sent to operational personnel. And as I said, system is working almost 8 years and very efficiently. Operational love it. because they don't need to do anything and just receiving information that something have happened and mitigation information attached. So are we ready for the future with this system? Let's discuss that. So with significant penetration of inverter in the system, what is expected? We expect significantly increased frequency range. Before it was typical electromechanical oscillation range. Now it could be anything. Then we have established PMU infrastructure. Currently, we are using 30 samples per second, but in near future, we will shift it to 60 samples a second. However, these measurements are good for monitoring oscillation, probably not higher than 5 to 7 hertz. Higher frequency are not correctly monitored by this PMU. So existing PMU are not ready for high frequency oscillation. Then initially oscillation source was pretty good term describing objective, what we are trying to accomplish. These days it's not anymore, because for new type of oscillation, significant portion would be related to control interaction. So that means there is no single injection point of external energy in the system, but it could be several system components interacting and causing oscillations. So a future process component looks listed on this slide. First of all, practical solutions should rely on data-driven methods. Model-based methods will not work in this situation. That is definitely a conclusion from whole previous experience. And so far, energy-based methods, and there is a whole family of this method, but I will be talking mainly about dissipating energy flow and complex dissipating energy flow as used at SSO New England. So far, this method show pretty good performance. Then we should rely on point of wave measurement, but not on PMU data for the future implementation. And as a good news, Schweitzer now producing this device, Cell 765, which provide continuous stream of point on wave data with 3000 samples a second. And also with this sample rate, OSL method should use distributed implementation. So old strategy, when all PMU data stream to in real time into central location and then processed over there, most likely will not work in the new environment with point-on-wave data, because you have to load communication system 100 times comparing to PMU, and that is not really a good idea. So that means OSL technology should be based on distributed implementation. And also correction to objective. Like before, for forced oscillation, objective was to find the source of oscillation. Now objective is shifted. We need to find system components most efficient for mitigation. So that specifically means find system component significantly contributing into oscillations. And that is schematic diagram how it should look like. So on the substation level, there should be a process which is processing local point-on-wave data and generating results. And then all these results should be sent to central location, where all combined results analyzed from system point of view with all type of analysis, like visualization of dissipating energy, pattern recognition, participation of oscillation, and so on. And column on the left and the right show details on implementation. We will not touch that at the moment. So what is important is identify what should be a property of oscillation source locating method. I'm not saying that what we are using is the best forever. It's open area, but at least what is important is to identify what should be a property of the method. So, first of all, this technology should identify system components most efficient for mitigation of oscillation. And efficient mitigation means ability to control damping of oscillation. And so far, a family of energy-based methods, there is a whole family of the method. And again, I will be talking mainly about these two versions. And those two versions satisfy those requirements, efficient mitigation, because by definition, energy-based methods are tracing system components most significantly impacting damping of the oscillation. So for the history, energy-based method, first publication from Tsinghua was related to 2013. Then dissipating energy flow was actually introduced in 2017. And that is a formulation of two components. Then next level was developed in 2022, when the same energy is calculated as a four-component function. And now the most recent development this year, then dissipating energy is computed a little bit different. And there is paper which is available in the archive. And this paper currently in the review process for transmission for power transactions. That dissipating energy flow method DEF was implemented at ISO in England in 2017 in production system, and that is version 1. In 2024, upgrade was to CDEF method, and newly developed SSO-CDEF method was, efficiency of that method was demonstrated on simulated point-on-wave data. And we expect that that approach will be a basis for production system for the next generation. In terms of the theory, everything is starting from conservation of energy function. Then this energy function is split to imaginary and real parts. And formulation of complex dissipating energy is formulated as a combination of imaginary and real part of the energy. Then in this formula, all oscillatory terms cancel each other. And we are interested only in non-oscillatory terms in any branch of the system. So at the end, final formula look like that. So dissipating energy, so contribution of system component into the damping of specific oscillation is computed as four terms, where the K is empiric parameter, external parameter. What is the specific of point-on-wave? In PMU, we were talking about oscillation, and here it's denoted by omega, large omega, which is frequency which was defined in rotating QD frame, which is rotating at fundamental frequency. So if you plot frequency spectra, oscillation look like that. So specifically 4.55 Hertz in QD in rotating coordinates look like that. However, if you convert it to ABC, point-on-wave coordinate, that frequency is translated into two frequencies, subsynchronous frequency and supersynchronous frequency. And that's how it look like in the power spectra density plot. So what is important? So if we are dealing with point-on-wave, you have to consider these two components, subsynchronous and supersynchronous, like two pieces of the same process. And they should be processed simultaneously and together. And results should be summarized to make a judgment on the source or who is participating in this oscillation. That is important because subsynchronous and supersynchronous component are just what we see from the same physical process. So it's different enumeration or different ways how to see the same physical process. So, and typically what have happened, if you model, let's say you are modeling EMT type of simulation, and you change parameters of the physically representative model of inverter, then you will see a pair and sub and supersynchronous components, which is really a reflection of physical process. But at the same time, we know that there exists of subsynchronous resonance, which is not caused by inverter, but really it's resonance involving network components in the system. In this situation, you will see only one component, not both. So what is important that if you are using point-on-wave method should account and should consider a possibility of both situation. When you have a pair, linked pair of two oscillation or a single oscillation. So that should be accounted in the algorithm. So for new this method, subsynchronous SSO-CDEF method, derivation was exactly the same as for complex DEF method. But at this point, when energy is defined as a sum of imaginary and real component, instead of using QD frame components, all quantities converted back to ABC frame, and at the end, the following derivation is obtained. So what is principally important here, for assumed assumption, initial assumption that we are dealing with positive sequence of data, final derivation for SSO-CDEF and CDEF method are identical because they're using exactly the same model. And when we are talking about phasors here, it's not actual phasors obtained from PMU with all limitation related to that. Here we are discussing clean mathematical transformation from ABC to QD frame, which doesn't introduce any problems and discrepancies. So then for testing, what have been done, we took 14-bus system with a simulated environment, which was created by Imperial College, and there is a reference. It's open source setup. And over there, they have three grid following inverters in buses 11, 12, 13. And there is EMT simulation in MATLAB with 500 samples a second. It's output results, but integration step is much smaller, of course. So synthetic point of wave measurement were obtained from EMT simulation at 500 samples a second. So, and we used OSLP2 version 3 developed by Sony England as a computing engine for calculation of source location. So then next few slides, we'll discuss several test cases in that system. Case number one. In this case, parameter of current PLL control bandwidth for all three inverters were modified in order to create oscillations. And inverter 12 was modified worst, so you would expect that that inverter would produce the worst results. So in QD frame, you see there is 8.6 Hertz oscillation and some harmonics also. And NBC coordinates picture is more complicated, look like that. So on this graph, you see results of two methods, CDEF and SSO-CDEF, and they are practically identical, as I said earlier, because with given assumption positive sequence, symmetrical calculation, results should be the same. And on these graphs, on vertical axis, it's dissipating energy. And when it's positive in the current sign notation, that means it's negative contribution into damping on the system. On the horizontal axis, A means a generator, L means load. So on the horizontal axis, there is contribution of all injections into the system, 14-bus system, all loads and all generators. Okay, from that picture, it's clearly seen that all three inverters shown as negatively contributing damping, and inverter 12 has the largest contributor. And below graph show empirical index, which means that index is viewed as index showing participation in the oscillation, and formally shown here. So all three inverters are shown as significantly participating in this oscillation. Next example is interesting, control interaction. And here is control interaction of grid following inverter with AVR at synchronous generator A1. What have been done in this case, megawatt output of all inverter was significantly increased, and output of generator 1 was significantly reduced to balance the system. And that resulted in an oscillation 1.47 Hertz. So for results of dissipating energy, what was interesting, the generator synchronous generator A1 is shown as a source of negative contribution into damping, negatively contributing damping. And all three inverters positively contributing damping. At the same time, all four these components are very significantly participating in the oscillation. And what does it mean? Expectation is the following. If you participate in the oscillation, that means modifying your control or operating conditions could be effective for changing damping of oscillation. And that was verified. So what have been done? If you reduce AVR on the generator, oscillation became damped. Or if you reduce PLL bandwidth of any of inverters, effect will be the same. So basically, these results are at least qualitatively correct, indicating that if specific component significantly participating in oscillation, it could be efficient for mitigation. Next example. Parameters of IBRs were adjusted of all three IBRs to generate 22 Hertz oscillations, and that's how they seen and fragment of time domain simulation. So all three inverters were identified as negatively contributing damping. Then the energy-based method claim that dissipating energy is proportional to contribution into the damping. And that test intended to verify that. In order to do that, what have been done? Each of the parameters, bandwidth of any of inverter was reduced by the same quantity. Basically, the same control actions was applied for each of IBR, one a case. And that picture show how much was changed damping of oscillations. A real part of oscillation, how much was changed. So the same control actions caused the same change of real part of eigenvalue of this mode, 22 Hertz mode. And the most impact was obtained by applying control at inverter 12. And you see, dissipating energy of that inverter is the largest. Basically, this ratio of changing real part of eigenvalue is very consistent with dissipating energy from the method. Next example, grid forming inverters. In previous examples, all inverters were grid following. Now, two additional grid forming inverters were added in bus 4 and 5, and their parameters were modified to create 4.55 Hertz oscillation. You see. Then, dissipating energy results show that one of those, specifically inverter 5 negatively contributing damping, while inverter 4 is positively contributing damping. But at the same time, participation analysis show they practically equally participate in this oscillation. So as I said earlier, if they participated in oscillation, that means you should expect that they could be efficient in mitigation. And that process was verified. So voltage control bandwidth of one of these two inverters was reduced, changed by 10 Hertz, one at a time, and that is impact on eigenvalues. So basically the same. So controllability or efficiency of changing control of both inverter is about the same. And that is reflected really from the values of dissipating energy and participation factor. So that is a type of confirmation that those information are useful and consistent with initial claim. One more result showing robustness of the method. As I showed earlier, a formula for dissipating energy contains parameter K, which is roughly ratio between resistance of the network to impedance of the network. And Imperial College tool, which was used for this type of analysis, have a capability to analytically estimate eigenvalues or actually contribution of each component or each control on damping of specific oscillatory mode. And this picture show results of this calculation. So, and results, and what is important, that only inverter 12 and 13 were parameter, only these two were modified. And you should expect that only these two should be sources of negative contribution into damping, but not the rest of the system. So calculation of eigenvalues from Imperial College tool confirmed that conclusion, that only inverter 12 and 13 negatively contributing damping, but inverter 11 still provides positive contribution to the damping. Then OSL method was run, and those are results of OSL method by variation of K. And that picture show robustness of SSO-CDEF results if you change K. So all these results are correct as long as negative contribution, the damping for 12 and 13 remains negative, but inverter 11 provides positive contribution. And this shaded area show when it's happened. So what does it mean? That all results, at least qualitatively, are correct if K value could be selected from 0.14 to 0.54, specifically for this model. It's pretty wide range. Okay, and last slide. All previous examples were related to natural oscillation caused by modification of parameters of control. That slide shows results of classical forced oscillation when external signal was introduced as a sinusoidal shaped signal at 7 Hertz, was introduced as additional input to reference points for megawatt control, active power or reactive power or voltage control on each of the 3 inverters one at a time. So top row show results for injection of external source in active power control, and bottom row show for voltage control. So as you can see that all results pretty clearly and correctly identify source of oscillation. No any doubts. It's very robustly results show finding the source of forced oscillation. Okay, so what is expected as the challenges for the future implementation? And again, I'm talking from ISO point of view because that reflects not purely theoretical development, but robustness of actual implementation. First of all, based on experience by using PMU data, what is important is to avoid false alarm or false identification. And what does it mean? That means if you use bad PMU data, you may produce bad results, garbage in, garbage out. So that's why in our current production implementation, very significant portion of the process is devoted to filter out bad PMU data. So, and similarly, we expect that this similar process should be done for point-on-wave data. However, how bad and what type or what form of bad could be expected from point-of-wave data, it's unknown now because we do not have this data. And it will require significant period of observation over time to detect what is bad and develop algorithm filtering out all these processes. That is quite important for robustness. And again, if you are in the university environment and working offline, it's really human is capable to find bad data because human eye is very good pattern recognition tool. But here we are talking about process, fully automated process without any human in the loop. And this process should not generate false results. Okay, then another piece. Both methods described, used for analysis in this presentation are using bandpass filtering. Okay, and if you use QD frame or traditional PMU data phasers, filtering is not a big problem over there. However, if you use point-on-wave, it could be problematic because you will always have very huge peak at fundamental frequency. And if you're analyzing frequencies at, say, less than 1 Hertz, you will have two very small peaks around 60 Hertz, and you need to filter out these peaks. So presence of huge peak at fundamental frequency could be a very bad factor, which may significantly impact your numerical results. So that's why be aware that filtering should be very carefully designed to avoid numerical problem. As a practical implementation, what is useful? So if you have frequencies oscillation at low frequency, it's better to use CDEF method. But if you have high frequency oscillation, there is no problem to use SSO-CDEF. And the last problem, but not the least piece, is that so far energy-based methods using assumption that we are dealing with positive sequence of data, sequence of data. However, if frequency is exceeding fundamental frequency, we have an issue because what we observe now in point-on-wave became negative sequence. And that is practical example and data, thanks to Wilson, who provided practical data from flicker measurement. On this data, oscillation frequency, which is metered in phasor, is 177 Hertz. But if you run power spectra density for oscillation spectra in point-on-wave data, you see peak at 117 Hertz and 237 Hertz. And that could be viewed as subsynchronous component and supersynchronous component of the same process because they are completely within definition of those components. However, if you look at the details of filtered signal, then subsynchronous component became negative sequence because you see color A, B, C, and if you look at the sequence actual A, C, B, it's negative sequence. However, supersynchronous component, everything is fine. A, B, C. So that means you have a component which have negative sequence, and all energy-based methods currently developed for only positive sequence. So that situation requires some investigation. And that's what I have so far.